probably looks pretty stupid, but did you know it's actually possible for tiny particles to go right through solid objects? That's just one of the amazing effects of quantum mechanics. But to understand that, you'll need to understand waves. What is a wave? A wave is basically something that repeats itself over and over again redundantly with repetition. This is a wave because my hand is moving back and forth and back and forth. Ocean waves are waves because the water moves up and down and up and down. Ripples in a pond are waves because there's ripple after ripple after ripple after ripple. And waves like that spread out, like the ripples in a pond, have an interesting property called diffraction. When those waves meet a wall where there are only two tiny little slits that they can get through, they become two separate waves. And as those waves spread out and run into each other, wherever two high points meet, they add together to make an even higher point. And wherever two low points meet, they add together to make an even lower point. And wherever a high point and a low point meet, they cancel each other out. So we get some places where there's no wave at all, and some places where there is wave. And scientists found out that light actually diffracts. So when you shine light through a bunch of tiny slits, it creates a pattern where there are some places where there's no light and some places where there's a lot of light. So scientists were sure that light must be a wave. But a new experiment would rock the world of physics forever. Let's imagine that light is made out of water waves, and bowling pins on the beach represent these tiny particles called electrons in a piece of metal. Now, if the waves are few and far between, you'd expect that it would be hard for them to knock over the bowling pins. But as if you made them big enough, then it doesn't matter how far apart they are, they'd still knock over the bowling pins. But that's not what happens with light. No matter how big you make the light waves, if they're not close enough together, they don't knock any electrons off the piece of metal. Now, let's imagine instead, if light were a particle, like a tennis ball, and throwing a lot of tennis balls is equivalent to having a bigger wave, and throwing them harder is equivalent to having the waves closer together, then if you don't throw a tennis ball hard enough, it doesn't matter if you throw 1 or 1,000,000 tennis balls, you're not going to knock over any bowling pins until you throw the tennis ball with enough energy. And that's the same thing that happens with light in this experiment. So it seems to indicate that light is a particle. But particles don't diffract. Well, which is it, a particle or a wave? Well, this crazy-haired scientist named Albert Einstein said, if it behaves both like a particle and like a wave, then it must be both a particle and a wave at the same time. Yeah, scientists then thought he was crazy, at first. But it's the only explanation. Somehow, light is both a particle and a wave. Now, if light can be both a particle and a wave at the same time, then why can't particles like electrons be both particles and waves at the same time? Well, scientists did an experiment, and they shone electrons through slits, and it created a diffraction pattern. Even when you send them in one at a time, it still creates the diffraction pattern. Now, this raises an interesting question. If an electron goes through one slit, and it creates the diffraction pattern, okay, but if the other slit is blocked up, the diffraction pattern stops. Well, how does an electron that goes through the one slit know that the other slit is blocked off and know to stop creating diffraction? Well, the answer is when both slits are unblocked, the electron doesn't go through one slit or the other, it goes through both of them at the same time. We shouldn't be thinking of the electron as a particle right now, we should be thinking about it as a wave. Now, you might say, well, why can't we just see which slit the electron goes through? The answer is, if we use light to see which slit it goes through, the light knocks the electron off course and we know where it is, but we ruin the diffraction pattern. We can either have the particle properties or the wave properties, but not both at the same time. So what does it mean for a particle to be a wave, like this, for example? Well, wherever the wave is really high, the particle is probably going to be there. Wherever it's lower, it's less likely, but still possible, and where it's zero, the particle is definitely not going to be there. We can also tell the energy of the particle by how often the wave repeats itself. So for a wave function like this, we can measure how often it repeats itself and know the energy really well. But we don't know the position very well. It could be in 1,000,000 different places. Whereas with a wave function like this, we know the position really well. It's probably there. But it's hard to measure how often it repeats itself. It doesn't really repeat itself exactly. And so we can't know the energy as well. The better we know the energy, the less we know the position. And the better we know the position, the less we know the energy. This effect is called the uncertainty principle. Another interesting effect is called quantum tunneling. If we have a wave function like this, and there's a wall, a particle can be on one side of the wall, but there's a possibility that it'll appear on the other side of the wall. So a particle can actually go through the wall without touching it at all. Quantum effects seem really strange to us because they're so small that they're only noticeable in teeny objects like electrons. But this is the way the atomic world works. It's strange, but amazing.